All right, so let's just draw this then. So hybridization of molecules containing double and triple bonds. Let's use valence bond theory and hybrid orbital theory to draw pictures, orbitals explaining the bonding here. So the way I do this is I draw like this, and this is what I've been drawing. So carbon is sp2 hybridized, excuse me, trigonal planar. So I draw the three equivalent sp2 hybridized orbitals around each carbon. I've just drawn a sigma bond. What goes here, 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 and here, those are all 1s orbitals. Those are also sigma bonds. So this picture has explained all 1, 2, 3, 4, 5 sigma bonds in this molecule. We have to explain the pi bonds. So what do? Oh, we go back. We fill it with color. We have adjacent p orbitals left over. Those guys overlap, and that forms a pi bond. So this is a picture explaining all of the bonding using hybrid orbital theory and valence bond theory for this molecule. This guy, let's do next. So let's have a think on him. So this is a molecule called formaldehyde, all right, used in embalming bodies. But what's the shape? What's the hybridization on carbon here? He's sp2 hybridized because he has three things around him, right? Three sigma bonds, sp2 and trigonal planar. Trigonal planar. So then from that, we can explain all the bonding. So C is sp2 hybridized. So I expect to see three equivalent sp2 hybridized orbitals. O is a little trickier though. What's the hybridization on O? He's got a sigma bond, but he's got two lone pairs. So really, he's the same. He's trigonal planar again. He's the same thing. So O is trigonal planar. But in this case, what's in these sp2 hybridized orbitals? Right, this is where the lone pairs are. Right, this is their little home. Here we have two sp2 hybridized orbitals overlapping. That's a sigma bond. All right, and remember, we still have our p orbitals. I have them in this picture. Let's draw them here. Here they would be upright and parallel like this. Right, and what we've seen is they've shown this kind of, we'll call that a goldy color. That's the overlap showing the pi bond. All right, so we can do the same thing here. If I was to draw this guy, I'd draw a C, I'd draw him trigonal planar, I'd draw an O, trigonal planar, sp2 hybridized. I put my lone pairs here and here, overlap with some 1s's, forming sigma bonds to h's. So now I have 1, 2, 3 sigma bonds. I have to explain the pi bond by the overlap of adjacent parallel p orbitals gives me my pi bond. So really, these two things have the same structure, right? In this one, you've got H's and C's overlapping in these hybridized orbitals to form sigma bonds. In the case of formaldehyde, you've got lone pairs in them. Same thing. Let's look at sp examples. So what we said was here we're going to take the ground state electron configuration. We're going to promote one electron. So each orbital has one electron. We have one s and three p's. We're going to hybridize now an s and a p. That takes one s and one p. Mix them up. Now I get two equivalent sp hybridized orbitals. And let me draw this quick. So the way I think, whoops, this guy, let's take this guy like this. And then we'll put this guy like this, and we'll put this guy like this. If these guys mix, it's kind of like you're making this guy more S-ish, and you're making this guy more P-ish, and now you're equivalent. So you have these two. Bad work. So something like this, right? These are sp hybridized orbitals coming together in a linear conformation. But important thing on this slide is what do we have left over? Two p orbitals, and they're these guys. So we're going to take advantage of those to form some pi bonds. So here we have acetylene, or ethine. Carbon has two sigma bonds around it, so it must be sp hybridized, period. Carbon, here's my sp, on carbon. Direct overlap here forms sigma bond. Nice work by you. Here, overlap of sp and s gives me a sigma bond. All right, we have to explain the p. Use the p orbitals to explain the pi bonds. And to do that, remember we had two p orbitals left. One was straight up and down, right? And the other one was kind of into the page. So this picture's not the best. But if I was to draw it here, and this gets really messy, here's these p orbitals overlapping, right? Here's the py. That overlaps, forming a pi bond. The pz is into the page like this. Those guys would overlap. And if it's more pretty, it looks like this. I guess it's kind of like a hot dog with a bun cut into quarters or something. I'm not sure. But what you're getting is you're forming these shapes because you've got the p orbitals this way and the p orbitals this way, overlapping. Pi bonds. So if we were to draw that here, like I said, this gets kind of messy, but all right, so I'd say C is sp hybridized linear. So C is going to look like this. C is going to look like this. How do I, let's finish out the sigma bonds. So here's a sigma bond, the direct overlap of two sp hybridized orbitals. Here are my 1s's and sp, also sigma bonds. We've explained all the sigma bonds now. We have to do the pi bonds. And so again, this is where it kind of gets ugly, but I'm going to have p orbitals this way and p orbitals this way, right, directly into the page. These guys are going to overlap, these guys are going to overlap, and that is 2 pi bonds. Cyanide, oh, she needs a negative charge, is the same thing. Yeah, so we just draw it there. So let's just draw the same thing. C, sp hybridized. Here's N, also sp hybridized. What goes in this sp hybridized orbital? Whoa, a lone pair, you were right. Here, another lone pair. And then we explain the rest of it by making these big, messy p orbitals come together, p orbitals come together, overlapping, pi bond, pi bond. Nice.